All right, so I guess the room is getting full, so we're ready. And so this lecture, and I would say the topic of today is going to be polaritons. And in the morning, you'll hear more about theory of polaritons and how to describe them and simulate them and calculate them. And you have some exercises on that. And then in the afternoon, Professor Initio will tell you more about them, I guess, from an experimental perspective. But before we do that, because I've heard that maybe the last 2 days was a lot of math and a lot of equations and a lot of concepts discussed. So do you have any doubts and questions or comments? And I will wait until I hear at least one. So could be the longest 3 hours of your life.
Lectures are not allowed.
No.
So many questions.
Yes.
Okay, so we have seen a lot of ab initio considerations of light matter coupled systems. How close are we actually to sitting down on a computer, doing a calculation, and a matching experiment?
Okay. I think that's a general question for every ab initio kind of method. So I think we can definitely sit down and run a simulation, and you will do that. Now that it matches the experiment, that's another story, especially because of the problem of quantifying the light matter coupling. And so you have seen yesterday from Mark that we have a theory that in principle can account for that. And in like standard linear response, which we will see today, that works. So you can get the right size of the Rabi splitting in most cases. But then we still don't know what happens for what we will introduce again today, light matter hybrid systems, where it's not any more polaritonic physics, but it's more something like related to the coupling of a ground state to the fluctuations of the electromagnetic field. So for that, we can do simulations, but the light matter coupling is still a parameter. But for excited state properties, you will probably see that better at the last tutorial. You can actually get pretty accurate Rabi splittings and line width of polaritonic peaks and stuff like around that along that line. Yeah, more. I said one comment, but that was too fast. So anyone else from this side? I didn't hear your voices the past 2 days.
All is clear.
Yeah, but I'm sure it's not, so I'll just wait. Yes.
Okay, so the electric field H bar omega alpha is characterized or given by its cavity shape. But in the equations, formalisms, we never mentioned how the cavity shape connected to the field distribution. Is that possible to be explored in the simulation? Or?
Yeah, so that's a true statement. And so yesterday you have probably seen or glanced over like the formalism that allows you to do that. And it's definitely possible. And so it does not depend only on the geometry of the material, but it also depends on the type of the material, as you have seen yesterday. And then you can, for example, calculate electric field strength using transmission transfer matrix method. And from that, you can also build the Green's function, which you have seen yesterday introduced in macroscopic QED. And this Green's function is what allows you to define quantized electromagnetic modes where the mirrors are effective. So you don't want to describe the complexity of the mirror in terms of microscopic degrees of freedom, but you would rather dump them into an effective mode or multiple modes. And the coefficients of these modes you can actually get from macroscopic QED if you want to include losses. But if you don't want to include losses, which you should always do that, you can do that. You can calculate the fields from transfer metrics, like, for example, what you've done in the notebook yesterday. So there you only calculated the reflectance spectra, but you can, in principle, from the same method, get the field, because the transfer metrics method is built out of the interference of the field amplitudes. So you can actually calculate the field amplitudes. From those, you can get the field strength.
It's a multi-scale workflow. It's a multi-scale workflow.
It's a multi-scale, exactly. So it's a multi-scale workflow where the mirrors are treated in a macroscopic way, but you can still inform your calculation with the dielectric properties of the mirror, which is the important part. More? Also, this side is allowed.
What is the most extreme example you've seen of the properties of matter and light changing when they hybridize?
In theory or in experiment?
Either.
I mean, you will hear more about experiments, and I don't know if you will talk about the superconducting
I have PowerPoints on that.
system.
I don't know if I get to that.
So I guess that's one case where you can you will hear more hopefully about it, but you can change the superfluid density of a superconductor by placing it on a cavity. Now that is not a standard cavity; it's a polaritonic cavity. I'll actually talk about that briefly. But there you can really see changes in macroscopic properties of a big system due to the coupling of the electrons in this system to bosonic degrees of freedom. So that's one. Then there is another experiment where you can see in a Fabry Pro like cavity transition from a metal to insulating phase, and I think it's still debatable what is the mechanism there. It's not necessarily only quantum fluctuations, but also maybe thermal fluctuations. But that's those are two examples in the condensed matter community. But then there are many more on in polaritonic chemistry where you can see changes in reaction rates. And I cannot remember the kind of molecules that they looked at, but the idea is that like you have a reaction that, for example, A plus B that brings you to C or D, and then through the cavity you can alter the reaction landscape and maybe favor reactant product C to D or vice versa. And this has been demonstrated also by different groups. And then you have seen a lot of the results from Professor Junkono on Monday that showed that you can achieve ultra strong or deep strong or infinite strong coupling in these magnetic Landau polariton systems. So I think those are the ones that come from the top of my head, but you will probably hear more later. Anything more? No? One last one. So the theory was all clear. Was it clear why it was necessary to introduce macroscopic QED, for example? Or why do we, how do we get resonances out of interference, like in the transfer metrics? Or why do we quantize the field?
Well, the previous lecturers were just perfect, right?
Yes.
Thank you so much.
One last one, and then I will not bother you again for the next 10 minutes at least. Yes. So why was it necessary to do the full quantization again in the presence of mirrors, which are made of real matter? well, we're not just fine with doing like free space quantization and that's it. Yes.
Epsilon of omega can become complex because you have absorption.
Yes.
You no longer have an orthonormal function set on your Hilbert space. Mode quantization becomes challenging.
Yes, indeed.
Take into account matter to make everything Hermitian again and to have a well-defined theory.
Yeah, that's a good point. And in practice, conceptually, what you're trying to do is that you want to be able to describe losses into some environment, which you cannot explicitly include in your system. So you have to come out with a way that you can dissipate energy in an Hamiltonian framework. And that's the whole point of MQED. And the complexity then arises from the fact that you have so many infinite modes that you need to take into account, and you have to sum also over all the possible energies of the mode, and not only, for example, the momenta. So that's a little bit the compromise that one has to use, but that works, and then you can actually get quantities out, which are useful, and you can use for the calculations. And you'll use that, especially in the last tutorial. Okay, so I think I pushed you quite a bit. So let's move on to today's lecture. I'll ask you more questions. So what we will do today, at least try to get through all of them, if we have time, are these following points. So first of all, we have talked about quantum description of light and matter, but in fact, a lot of the polaritonic properties are already described from a Maxwell perspective. So you don't need quantum at all. And I think it's important to understand this. I mean, when I got into the field, I knew about polaritons from textbooks, but I always thought that you needed a quantum description to get polaritonic Rabi splitting and polaritonic branches. But in practice, actually, in many cases, you don't. And I think it's important to see why that is the case, and how simple it is to actually get it from Maxwell. And then we will derive a similar behavior in linear response from ab initio QED in a simplified model. And this is the case where the model is useful, but it's also not the last resource that we should rely on. And then I will also try to motivate why it could be convenient to actually do a quantum treatment of polaritons. So even though we can do them through Maxwell, it's actually quite handy to talk about polaritons in a quantum way. And then finally, also, I will describe, and you will do an exercise on that, how you can actually start discussing about light-matter hybrids instead of polaritons. And these guys here are actually not describable from a classical perspective. Okay? So one of the very first questions was, what is a polariton? I think that was on Monday. And I think you have heard quite a bit about them from June. But in general, a polariton is any quasi-particle where you have a strong coupling between matter excitations, which can be electronic or phononic, or vibronic if you're in a molecule, and the electromagnetic field. So these are just a few examples of polaritons, which I think I have stolen probably from the Polaritonic panorama that maybe Dimitri will tell you more about later. But for example, you can have polaritons, which are a mixture of plasmons and electromagnetic field. You can have polaritons, which are a mixture of phonons and electromagnetic field. You can have polaritons between electromagnetic fields and Cooper pairs. So even like the Cooper pairs in your superconductor, they can form polaritons. You can have magnetic polaritons, so magnon polaritons, so on and so forth. And the whole idea of the polaritonic physics, at least in excited states, is the following. So take an example of a matter excitation, for example, an accident. I'll talk more about that later. And plot the dispersion of this exciton as a function of the momentum. Now, if the scale of this momentum here is small compared to the dispersion of the exciton will look like a flat line. And then you take a free space photon, and the dispersion of this free space photon is a line, right? So this is just the energy of the photon as a function of the momentum. Now, if the two degree of freedom start talking to each other, they will hybridize. And this hybridization will lead to the formation of two branches, a lower polaritonic branch and an upper polaritonic branch, which are split by a certain amount, and this certain amount is called Rabi splitting. So the whole physics of polaritons, at least in linear response, is really based on the formation of this fissure. And you can find different regimes of coupling. We will see that based on how big this polaritonic gap is compared to different scales of the system. And I mean, June has already shown a lot of examples of polaritons in the first lecture from an experimental perspective. So this can really be observed. So, yes, I literally took a snapshot of one of the slides. So I wanted to make sure that you were aware of that. But I mean, in all cases, maybe it's a little bit less evident here, but you can see that you have the formation of these polaritonic branches and for different kind of polaritons. So you can really couple a lot of things with light, which is nice because that means that if you can couple to these things, potentially, if you couple strong enough, you can change the properties of the material. Okay. So now, the first step is to understand how we can get them from classical physics. Because if we are satisfied with the classical physics treatment, why do we need to do quantum? And let's consider the case of a bulk material. And let's consider how an electromagnetic wave propagates in this bulk material. Well, what you have to solve, and this you have seen already a bunch of times, is this Helmholtz equation. And you can see here that in the presence of matter, you have to take into account this epsilon. So epsilon is the response function of the matter. So it tells you how a certain electromagnetic field or electric field is screened by the presence of the electrons in your material. So this is frequency dependent. In principle, it could also be space dependent. But that's the form of the equation that we want to solve. And you can have two types of solutions of this equation. So you can use the relation that has been mentioned a couple of times, where the double curl here becomes this expression. And then you have two categories of solutions. You have transverse waves. So this is the case for which the propagating wave vector is orthogonal to the electric field. And so that means that you can remove this term from the equation. If you remove that term from the equation, you're left with this one only. So the Laplacian of E equal to omega squared divided by c squared epsilon E. Now, if you Fourier transform that expression, the Laplacian of E will bring down a k squared. Right? So nothing else. So you get a k squared, then you get a c squared from the other side. And this one has to be equal to omega squared epsilon. That's it. So that's what you get out of the transfer wave solution. And this one is a relation that you can see connects the omega to the momentum. So it's a dispersion relation. Okay? So if you are able to invert this, then you can get an explicit dispersion relation for the bulk case. And we will see this is actually the bulk polariton you would expect. And then the other solution is the one associated with the longitudinal mode, where now is the divergence of D that is equal to 0. And this longitudinal solution actually is satisfied when epsilon itself is equal to 0. Okay, so these are the two solutions that you can expect, and it's a general form. Now let's take the case of a model material. And the model material now is described with a Lorentzian dielectric response. So you have seen that yesterday, you have also plotted it. And let's imagine for now that, for example, this Lorentzian is associated to a phonon resonance. Okay, so then if that's the case, so and this Lorentzian is associated to a single phonon resonance, you can see that it's only, this expression here only has one pole at omega at 0. And the oscillator strength of this resonance is F. Okay. Now, if this is the dielectric response of your material, then you can plug into this expression into the transverse solutions, and then you get this expression here. And if you actually then invert this relation to find omega, you also have omega here, you get the following plot here. So let's walk through this plot. So first of all, you see that you have two branches. So you have this one and this one up here. And these are the branches that come out of this solution from the solution of this quadratic equation. Okay, so these are indeed the polaritonic branches. So you can see, I didn't mean to do that. Yes, so these are the two polaritonic branches. So you have the lower polariton and the upper polariton. And you can notice that these branches are reaching two asymptotes. So the lower branch reaches the asymptote which is set by the frequency of the TO mode. And the upper branch reaches the asymptote of the free photon line for I momenta. And it goes to the frequency of what we call LO mode. And you can see that this frequency here is different from this TO frequency. Now, just for the sake of for being complete, omega TO is called like this for many reasons, but it's essentially the resonance of the system of the Lorentzian. And LO is a renormalized resonance, if you like. So it still depends on omega at 0, but it has a renormalization from other quantities. And so, and you probably remember that June has showed the fact that in the strong coupling case, you can actually get a shift in the upper polariton value when it reaches 0. And this is exactly what happens, for example, in this figure here. So you can see that there is not only the Rabi splitting, but there is also a shift in the asymptotes of these two polaritons. And actually this value here, where the upper branch is intercepting the y-axis, is the energy of the other solution, the longitudinal solution. So that's why it's called LO. And this is the polariton that actually does not couple to the light field. This is a longitudinal mode. The field is transversal, so you can see that there is no coupling to the propagating mode. Okay, but its energy is affected by the macroscopic field that you might have in a polar crystal. And I will not say much about it, but this is what gives origin to the what is called in literature as LOTO splitting. Yes.
Can you review the model that gave us this solution again? I can't quite remember where the coupling was.
So the coupling is set by, so the solution is given by this equation, the two branches, and the longitudinal one is just the pole of this. So for this, you need to show, so for this, you need to keep this part and then write down the Poisson equation. I didn't have it in this slide, But the coupling, so this doesn't tell you anything about the coupling. The coupling is inside this epsilon. So the coupling in this particular model for your material is set by F, if you like. So F is the oscillator strength of your transition. So it tells you how much in this case, a phonon, if you want to consider a phonon, is oscillating when it feels the field. And this is a very simple description of a material. It's only a single resonance, but you can imagine that you can have a bunch of them and you can sum over all of them and you can still come up with a sort of dispersion. Probably not analytical, but you can still do that. But there are many examples, and we will see one, where you can actually isolate single peaks. So a single Lorentzian is actually quite good for many cases. And so in the case of a phonon, you expect 3 degrees of freedom because the phonon can oscillate in 3 directions. So you get 3 branches. 2 are split as polaritons, and 1 is the longitudinal one, which does not talk to light. Propagating light, yes.
In this case, we assume that the material essentially fills all of space, right?
In this case, it's bulk.
And the question we are asking is what electrical field are we calculating in this case?
So this is the electric field inside the material.
Generated by some excitation.
Yeah, the question is how you get in. And in fact, this is not practical. I will show the surface in one slide. But in principle, you could argue, okay, what is the solution of Maxwell's equation in an infinite bulk system? In practice, you will have to have a surface. So to couple onto these modes, there is an extra step. I will show that.
I don't know, but I think it's important to say that those are really intrinsic excitations of the bulk system.
Yes.
Then it's not that you need an external field to create them. It's like plasmons.
So if I would do spectroscopy of my bulk system,
This is what he will show you, but those are really intrinsic.
So they exist. The question is, how do you couple in?
It was just
Yeah, I like it. A lot of questions.
gamma equals 0.
Well, so gamma equals 0 defines the lines. Okay, the moment that you have a finite gamma, so that you actually have a broadening, these lines will be having a finite width. So this is just the solution to get the actual dispersion.
Also renormalize the resonance frequency, or
I mean, unless it's very big, it shouldn't.
Could you give me a comment why upper transverse polariton and longitudinal polariton can need to match at the gamma point? It's degenerate at the gamma point, right? That point.
In this case, the
Yeah.
upper polariton.
And the longitudinal one. Is there any physical reason they degenerate at the gamma point?
So so the thing, okay, but what is degenerate is not the TO itself, right? So the TO and the longitudinal mode themselves, they're not degenerate because the TO mode is this one, right?
Yeah.
And this one instead is the upper polariton that is mixed with the light. Okay, so I'm not sure if there is an intuitive explanation why that is, besides the fact that, I mean, if you solve this and you invert it, then the limit for omega going to 0 goes to this value here.
Right. Yeah, I know that.
And
I know the equation, but I understand the equation, but I just want to know what's happening in the.
do you have yeah, please go ahead.
Okay. Okay, this is a very intuitive, maybe just to give you the feel. Just take the following setup that Simone is talking about. You have the LO mode and the TO mode, and this is typical because you have a number of atoms in the initial, and you will get 3n solutions for the vibration. Okay? And then you ask yourself, if I don't do anything, the LO and the TO, they have to be degenerate. Okay? Then your question would have been better expose why the TO mode is lower, not why they are not degenerate, because they're always degenerate. But there is one aspect which is important, is that when you have an LO mode, it takes you only 2 lines to prove that the motion of 2 atoms in the LO mode creates a macroscopic electric field in 3 dimensions. Okay? And this electric field is the one that is screened and is internal. And this is what is the reason why you get the split. Because one is seeing the internal electric field created by the other mode, and the other is just the bare TO mode. And this gives you the split.
But I think the question was why this line goes to the LO. I mean, this one is, it's because of the macroscopic field, but this line here, which is also a transversal mode.
No, what I wanted to say is that if there was no macroscopic field, it would be degenerate.
Yes, yeah.
Then it's the opposite, is that they are degenerate always, and then due to the macroscopic field, you split one and goes down.
Right. Oh.
That's what I wanted to say, not it helps. And this is important if you go to the systems or the finite system. I don't know, are you going to show it?
Yeah, I'm gonna show it. But the point, okay, so the point is that like, so this branch actually goes to LO, but then usually when you observe them, you observe around the light line. So you always see a splitting anyways. Yes. Then, now, as it was mentioned before, there was another question.
It was just I wanted to say that the longitudinal polariton is a plasma, right?
Not yet, in that case. I mean, in that case, it was a phonon, and now we're going to look at plasmons. But it could be, but in that case, it was a...
It's not coupled with light, so why is it called polariton?
Why is it not coupled? So this we got exactly from the solution of Maxwell equations, right? So light is embedded in the theory, right? Yes.
What's Q0 again in that plot?
Q0
of the, like in the bottom left.
Oh, that's where the light line intercept the omega TO.
Oh, okay.
Yeah. Any more questions? Okay, so now before you ask, okay, that is the bulk description, but what happens in practice, right? So you actually will measure a material through an interface. And if you have an interface, you can still solve Helmholtz equation. And in fact, that's what you have seen yesterday with the transfer matrix method. And for a single interface, you can actually simply use the reflection coefficient from the Fresnel equations. So, and in that case, for example, if you have an epsilon1 and epsilon2 for 2 different interfaces, this coefficient is equal to this expression here. And what you have to look for now are the poles of this expression. So these are the points where the system would like to say something, because it's the points where you can have a resonance. Okay? So it means that you have a pole in the reflection, for example, from that interface. So it means that something has been excited. Okay, so then the poles are given by this one set to 0. Now you can do simply some rewriting where you define this kappa, and this will be useful, you'll see in a second, as the I times minus I times Q. So you can rewrite this equation like this. And then the solution of this equation is the following. Okay? And the polaritonic dispersion is again an expression like such. Okay? So if you solve for beta, which is related to the frequency, you get now this expression, which is different from the one before. You see that before you only have the epsilon of one medium, which was the bulk medium, but now you have 2 media involved in this expression. So you have epsilon1 and epsilon2. So it's very important what is the relation between these two. And how does the field look like? Well, the field look like this. So we have a stratified system, and the field structure that you get from the approach that you have looked at yesterday is the following. So for example, for the transverse magnetic mode, you have a field that looks like this. So you have that it has an X component and a Z component. So Z direction is perpendicular to the plane and X is parallel to the plane, but there is no Y component. So this is the transverse magnetic solution. And the X and Z are related by this expression here. But the important point is that this solution goes with this exponential here. And you can see that in this exponential, there is a complex part and a real part. Okay? Now, the complex part is in the X direction, and that's the propagating part of this solution. So that means that this wave will propagate in this direction. But it also has components in the other direction. And for example, you can see that this one is a real solution, and it will just give you an exponentially damped solution. So that's what we call surface polariton. And the surface polariton has the property that is arising at the surface. So it's a solution that exists because you have an interface, and it's exponentially damped. Okay, so this is the field profile away from the surface. And you can see that it decays exponentially. It decays with different rates outside in epsilon1 medium and inside in epsilon2 medium. And the nice thing of this polariton is that it actually allows you to confine light to a scale which is completely way smaller than the scale that you have from the wavelength of the light itself. Okay, so this is exactly how you can achieve subdiffractive confinement of light. Okay, so this is how the field looks like. And then an example of how to obtain this kind of polariton is the plasmon case. So now in the plasmon case, you have a dispersion which is not as Lorentzian centered at a finite frequency, but it's described by the Drude-Metal response, which you also have looked at yesterday. And then you can plug this expression into the expression that you have seen here. Oh, this one. So epsilon1, it would be, for example, could be like air. So that could be 1. And epsilon2 is the Drude model. And what you get is, again, dispersion where you see 2 polaritonic branches. And you will have this lower branch, which is associated with the surface plasmon polariton. And this is the solution which is exponentially damped, right? So this is the solution that is confined at the interface. So it's a bound mode at the interface. And then you have the upper polaritonic branch. And this branch goes when the momentum is equal to 0 to the plasma frequency of your material. Okay, so to the bulk plasmon energy. And instead, the asymptote of this surface polariton mode is again split from the plasmon bulk energy. And the value of this is related to the, in this case, this epsilon, this should be epsilon infinity, and the dielectric index of the other material at the interface. So if we choose vacuum, it's 1, but this could be another value. So the splitting is set by the dielectric mismatch between the 2 interfaces. Okay? So, and the solution that gives you a surface plasmon is only always at TM mode if you have non-magnetic materials. And the intuitive reason, and you will have to check on your own by using the Fresnel coefficients for TE and TM and look for poles. But the idea is that you cannot have TE modes because there is no surface charge which would support the discontinuity in the Z component of the electric field. Okay, so if you had surface charges, that would be different. But here, the assumption is that there are no surface charges. So it's purely arising from the fact that the bulk has a plasmonic resonance. And you put an interface. Questions? Yes.
So there's only essentially one mode, right? So for a
Yes.
given KZ, I only have the modes that propagate along the surface.
Yes.
So I would, if I would couple this in some way, I would sum over the parallel momenta.
Yes.
There's only one KZ.
Well, the KZ is what you sum to give you this dispersion, right? But there are many KX. So it's a propagating mode, then you can have a solution for different propagating wave vector. So you're not propagating this way, right? So you're only propagating this way. But to couple onto these plasmons is tricky. And maybe you will see later how one can do it, because you can see an important thing here, that this plasmon is below the light line. So it's slower than the light line. So you cannot couple from far field, because anything that you send from far field will have a dispersion which is on this side of the light line. So there is no way that you will intercept this line. So you cannot couple to that unless you find a way to fold this line back. And that's what you do with grating. So if you introduce a periodicity, what happens is that you start folding this line back and forth like you do for a free electron. And then suddenly you have solutions inside the light line you can couple to. On the other hand, what you can couple to is the bulk plasma. Right? So, and then for far field, that's what you see. If a material is reflecting light, you can see exactly that pole. Okay? Okay, so that's for, yes. Yeah, go ahead. No, go
I
ahead.
think it's in all the textbooks, there's the other one, the surface plasmon is the one that they write. Okay, they call it surface plasmon, and usually they write it as omega p divided by the square root of 2. And that's, you will get it in many.
Yes, and
exactly this analysis that Simone is telling.
And the 2 comes if this epsilon is 1. And so this one is 1, and this one is also 1.
And then you have many people discussing the same thing for spheres, another type of geometries. Then you get a geometric factor from what goes in the square root. Exactly the same. I mean, when you go to all the literature, that you don't get confused, because they distinguish those modes, but they come from the same one, which is just the plasmon frequency with an interface. So I think it's good that the way he presented.
Okay, so now that was like analytical, right? So you can get a solution from just solving Maxwell equations, but you can actually just use the transfer matrix to find other kind of polaritons, still just using classical equations. So the transfer matrix was based on classical Maxwell. And this is an example of a Fabry-Perot cavity where you have, I will show the cartoon, you have 2 gold mirrors, and then a material inside which has a Lorentz-like resonance. Okay, so you can set it up like you did yesterday, just by defining, for example, the dielectric function of gold, which looks like this, just a Drude model. You can take the dielectric function associated with an excitonic peak. I will tell what an exciton is in a second. Like this one. This one is set around 1 eV. And then you made the structure. You see here you have vacuum, then you have gold, then you have a spacer, the electric spacer, which is just a constant refractive index. Then you have the refractive index for the excitonic material, which is related to this one. Spacer, gold mirror, empty space. So this is the structure without the excitonic material. And if you just do the transfer matrix, and this is a second part of the exercise you had yesterday, you will see that you get several resonances, which are consistent with the standing wave conditions. But in a real cavity, so you see that, I mean, these resonances are not perfect, they have a width, and at some point, the material is not sustaining reflectivity anymore, right? So you cannot use a gold mirror to get cavity modes higher at a frequency higher than 3D, for example. Now you put the excitonic material, and the simple thing you do is that you place another layer in your structure, and you describe the excitonic material with a Lorentzian, and then you see that you go from one resonance to two peaks. And this is exactly the formation of a polariton, all classical. And if you do that as a function of momentum, so another way of seeing this is that instead of probing a q equals 0, where the light is perpendicular to the material, you can put an angle, right? And in this way, you can tune the qx. So if you, or now here it's called k parallel. So, but it will be the momentum in the plane, propagating plane. And then you look at the dispersion, you see that you get the splitting here that you see for this plot, line cut, but then this splitting disperses within the light cone. And again, it gives you two branches, okay? Whereas this other one is the resonance associated with this other peak, which does not split because there is no resonance there. And what is that actually? Well, what that is again, is the mixture of the excitonic excitation, which on this momentum scale will be perfectly flat. So it will be this line here. But because it mixes with a cavity mode from a Fabry-Perot, where now the cavity mode is not linear, it's a parabola. So it will be this gray line. So it's not a simple line, but a parabola. Then it will split into two branches, which will look like this. And there will be a lower polariton and an upper polariton. And this is the kind of exciton polaritons that you can see from many experiments on exciton polariton. Okay, so this gives you, from classical arguments, the typical picture of two polaritonic branches. Questions? And please, you can try to do this on your own with the script that you have been provided. Questions? Yes.
When you see these type of plots, you often plot the imaginary part of the reflectance. So if you see like these dispersions, it's often the imaginary part of the reflectance that's plotted.
Yeah, you can also plot the imaginary part of the reflectance.
I was wondering what would be the distinction and what would be more rigorously correct.
So when you plot the imaginary part of the reflectance, you can also look at what happens in this region below the light line. So you can also see the plasmon polaritons, surface plasmon polaritons, or maybe HBN hyperbolic polaritons you might hear later on. Yes.
In the next slide, when you show the exciton, the condensate of excitonic polariton.
Where is there a condensate?
Yes.
Ah, okay. Maybe I should have removed that word. Okay. No, okay. Yes, I can elaborate on that.
Can you comment a little bit, for example, in which condition or what's the consequence of that?
Yeah, I mean, that's an interesting question. And that's why also exciton polariton got popular, because what's happening here is the following. So if you have an exciton, the dispersion of the exciton alone is flat, at least on this scale. But in reality, it's a parabola of a free particle, and it has a mass. But the mass is related to the curvature of this line. So you can tell that the mass of this line is definitely larger than the mass of this other line. Now, the thing is that if you do Bose-Einstein condensate theory, you will see that the condensation temperature is proportional to the mass. And a smaller mass leads to a higher condensation temperature. So the reason why these exciton polariton have been becoming popular is because you can excite them, especially if you excite the lower polariton, where the mass is larger than the standard excitonic feature. And then you can condense them at a very high temperature. I think even at room temperature, as far as I can remember. So it's a trick to give a lighter shape to your exciton and make it condense at a higher temperature.
What can we do with that condensate state, isotonic polariton?
Well, that's a good question. First of all, you can observe it because I mean it's not easy to observe a quantum macroscopic phase, and the idea is that like it's once you have a quantum phase, it's very easy to manipulate it. So you can perturb it a little bit, and then without having to use too much power from your lasers or from your gatings and whatever, however you create this condensate, you can manipulate its properties at low power. Yes.
Why is the cavity photon dispersion parabolic? Thought we have a cone, a light line.
So the well, yeah, we didn't solve Maxwell equations for this cavity, but let's see. So what happens in a Fabry-Perot? And this you can find even by setting perfect boundary conditions, so that the electric field has to be 0 at the interface. You have standing waves, right? So this is the lowest solution. Then you have the solution with a node, and then you have another solution, so on and so forth. Okay, so and these solutions are such that Kz is proportional to n pi over L, and this is the distance between the mirrors. Okay, so now omega is equal to the square root of kx squared plus ky squared plus kz squared times c. Okay, now the thing is that this is fixed. Right, so this would be, if you use these solutions here, this is something that you can index with an index n. You can rewrite so now if you actually fix n, for example, to 0 or to 1 for the first resonance, sorry, then you get an expression that if you invert gives you exactly this parabola here. So you're just looking from the other side, right? If you look from k as an x-axis and e, then you will get the square root.
The magnitude of k or a component of k?
This is the components, right? So this is kx and ky, and this is one of them. This k is only in the plane direction, so is a k parallel. So you're plotting k parallel for a fixed kz, and this is giving you the square root. The expression that, depending on how you see it, it looks like a parabola in this axis.
Okay.
Right?
Thanks.
Okay. So now I've shown that you can actually get polaritons fully classically, right? And this is also a stolen statement from June slideshow, which is saying that, in fact, if one is concerned with linear spectra, which is what I've showed you so far, you do not need quantum theory for polaritons. So the question is like, why do we need to do the effort of making them quantum? Well, I have 3 points here. 2 of them are maybe we need to make them quantum. One is definitely we need to make them quantum. So the first 2 points are the following. So the first point is that if you want to investigate strong nonlinearities, then the quantum picture can be convenient, because often nonlinearities can be described as virtual processes in your excitations. So if the field is strong enough or the coupling is strong enough, you can activate virtual processes which you would not have in linear response. This you could describe with higher orders in your Maxwell equations, but you could also describe with extra degrees of freedom that you can excite virtually. So that's one point, and I'll show an example of that, and you'll do an exercise on that. And then it could also be interesting to know what happens in the presence of few photons, where the light that you're coupling in is really quantum because you only have a very small number of photons. And then finally, the idea is that if we really want to build a material in the ground state, which is different from the material outside the ground state, then we need to go for a quantum description, because the microscopic wave functions describing your material have to change. Yes.
I don't know whether, just to clarify, but it would also be the case if you look at another observable, right? Beyond linear spectra.
Yes, yes. So, and that would be the nonlinear case.
Okay, that means not nonlinear spectra.
Nonlinear spectroscopy, if that was
any
not.
other observable, like
Yes.
a current or so.
Yes. Okay, so that's the motivation. But a sure thing is that if you want to observe any of this, you need to make the coupling between light and matter strong. And what is the way of that we can do that? Well, you have seen how to quantize the field in free space. And in the exercises, you have also calculated what is the field strength, or at least the expectation value of the E squared in free space. And that expectation value scales with the volume of your box, 1 over the square root of the volume of your box. Now, the idea is that if you take a cavity and you squeeze it, you squeeze this free space in a smaller volume, then potentially you get a larger coupling. Okay? So that's the whole business of cavity material engineering. The point is that you take your field, which is there in free space, and you squeeze it. And by squeezing it, you increase the fluctuations strength, which go with the expectation value of E squared, which you calculated in the first exercise. And that's one way of enhancing the fluctuations. So this is from the notebook 1. Then you calculate for an harmonic oscillator the expectation value of E. You get 0. If you get the expectation value of E squared, you get instead something that is related to the 1 over the square root of B. The other route of enhancing the light matter coupling, you have seen this also in the previous notebooks, is by increasing the number of particles which are coupled to your electromagnetic field. So you have 2 ways. Okay, so you can squeeze light and you can increase the number of particles. And this is something you can definitely do in condensed matter systems, because there inherently you have a lot of particles, right? So for example, this is a sketch of a 2D material, and you can place that into a cavity. Okay, so now let's consider specifically the case of exciton polaritons. So in this case, you have an exciton. I'll say more about it, but this exciton is nothing else than an electron hole excitation. Okay, and this is embedded in a material, and you can have many of them. Now you place a cavity around this exciton, and the pictorial way to think about the formation of this polariton is that this exciton is coupled to the photon modes inside this cavity. Now the exciton can decay into the photon mode, create a photon. The photon can be absorbed into the exciton, and this process can go on and on. And this is what, in a quantum way, you can consider as a polariton. Okay, so you have this decay or exchange of energy of excitons into photons that leads to a new particle, something that can also be called quasi-particle. That's how we like to call effective particles in solid state physics. And this one is equivalent, the quantum equivalent of the classical polaritons we have seen so far. Yes.
Should I think about excitons as being spatially localized excitations?
Your excitons are spatially localized on a scale which is larger than the unit cell. So they're delocalized compared to the unit cell, but yes, depending on how tightly bound they are localized. So it's the closest excitation that you can have in a solid state system to an atomic excitation. Yes.
Do you expect the cavity to modify the fine structure of the exciton?
Yes, and I'll show that, and you can actually calculate it in one of the notebooks. What time is it? 10. Okay. Yeah, it's fine because the backup is to cut the last part, so you don't have. It's better to not go through all the material, but make sure that you interact. So now this is just to flash the complexity of the system. I don't want to explain this, although you have seen it already. I will walk through the terms. So this is the Pauli Fierce Hamiltonian rewritten once again in a different form. You have seen it in first quantization, you have seen it in length gauge, you have seen it in velocity gauge as well. But this is essentially the Pauli Fierce Hamiltonian written in terms of modes of your cavity and your material. Now you have an extended material. Also, your material can be described in terms of block waves, which you can consider as modes. Okay. So this Hamiltonian is made by these pieces. So you have the free electromagnetic field. Then you have the interacting matter. So here you can put all your electrons, all your interactions, and all the complexity you want. But because you have coupled to the light by the minimal coupling procedure, you have two terms. The paramagnetic term, also called bilinear coupling. And this is the coupling that comes from the P dot A term for each electron. Right now you have a system of many particles. You have to put all the electrons in. And here is just a rewriting of this term where you use second quantization. It doesn't matter. What it matters here is that the process is describing the creation of an excitation of a certain electronic transition associated to a certain electronic transition at the expense of creating or destroying photons. Okay? And these terms, they both contain it's beyond the rotating wave approximation, if you have heard about that, because you also have the process where you can create an excitation by creating a photon as well. Okay? So this is the full term. And the important thing is that this is a quantity that is related to the matrix element of the momentum. You can calculate that from any ab initio code. This one, A0Q, are the mode functions. And these mode functions you can calculate, for example, with macroscopic QED. So you have all the ingredients. And then the last term is the diamagnetic coupling. It's complicated, but essentially this is the term that gives you the number of particles times the A squared. Okay? And here, again, you can calculate the functions as you like. So it's a complicated problem, but it's also nice because you have complete degree of freedom on how to modulate this A0Q. Okay? It's a great theory, but it's yes?
Oh, why is the last term called diamagnetic?
Well, because this is associated to what we call diamagnetism. So it's what gives the repulsion of the magnetic field for a non-magnetic material. So it's an historical name, unless anyone else has a better.
It's a historical thing. Yes. The paramagnetic is usually not expelling. It goes along with the magnetic field, and the other one is counteracting because it's a square.
So it's like probably you have seen the pictures of these frogs levitating in magnetic fields, right? Yeah. The frogs are definitely not magnetic. So that's what gives rise to that. So if you have strong enough magnetic field, then you can levitate things because water is diamagnetic. Okay. Yes. So okay. Yeah, I wanted to say this thing that So this is nice. We in principle have everything, but the problem is that look at the number of sums you have here. You have a sum over all the cavity modes. You have a sum over all your matter modes, all the possible band transitions, the polarization. I mean, you can go on forever here. So this is impractical, okay? So how can we get away with a simpler and useful model? I will not do the derivation, but I will try to give you the gist of it. So the idea here is now that we have a certain cavity which has certain resonances. Like the Fabry-Perot resonances could have like these standing wave like conditions. So these seem to be quite isolated spectrally. So they happen at very precise energies. Okay. So would it be possible to take an Hamiltonian that describes specifically the coupling to one of these modes? So that's the question that we're asking. So now if we do the calculations, for example, with a simplified version of macroscopic QED, we can get the mode amplitudes, the ones that enter the Hamiltonian. Okay. And then if you plot them as a function of Q, in this case is the Q in the Z direction, you could do a similar plot in X and Y. But in Z specifically, these functions are peaked around specific value. Well, these are exactly the values that satisfy the standing wave conditions. Okay? So it's true that all momenta here should go into these functions, but there are some that are preferred. And there is a certain width to it. Now we showed in now not the recent paper anymore, but soon to come out, that it's possible to do an averaging procedure of this mode and extract a single mode out of this continuum of modes. Okay, so we can then rewrite the paramagnetic coupling as the total current inside your material. So this is the part that includes all the possible electronic excitations times one single bosonic degree of freedom per polarization. So this is just the polarization index at most you have two. And this prefactor here, which for the full description with all modes would go as the infinite volume of this cavity. Remember that here we're confining with a Fabry-Perot only in this direction, not in this direction. So if we want to argue with the mode volume, we would be like, okay, the mode volume is still infinite because in this direction the system is extended. But in fact, we show that by averaging, so summing over this, we localize our mode and it acquires a finite effective volume. So all you have to think about now is that you can map this complex electromagnetic environment into a single or few degrees of freedom. And those scale with 1 over an effective volume. And the effective volume, even for an extended system, is finite. Okay. I think I'll then write down the Hamiltonian now, simplified for one mode only.
May I just
Yes.
one thing, if I might?
Yes.
Just again to connect back to my lecture. So the rest of all the modes that are not changed are then put into the observable mass that you have in quantum mechanics. So they are not gone, right? They are there that you use anyway in your electronic structure or standard quantum mechanical collection. So it's really the difference again.
Yes. Yes, yes. There are a lot of details that one has to be careful about. And one of them is that like when you're summing over all modes, you need to remove free space. But it would take like 2 full days to go through that. So let's not do that. Okay, now I'll walk again through the same Hamiltonian as before, but much simpler because you don't have the sum over all the modes. So you have the electronic Hamiltonian. Now you have only one photon mode, which is this effective photon mode with a certain frequency. Then you have the diamagnetic term, A squared. Now it's explicit that it's A squared. And you have the paramagnetic term, where you have, in the case of exciton annihilation in favor of a photon creation, and then you have the complex conjugate. And you also can include the counter-rotating part. And this ones you can calculate. Now, after the break, I think, right? So it's 10:15 that we have a...
Perfect on time, yeah.
Yes. So after the break, you can look at notebook 8. And your goal is to reproduce the linear response behavior from a quantum model. And the quantum model is simply the coupling of an excitonic transition to a photonic single mode. Okay? And the goal is that you can actually show that you can get these polaritonic splittings. And now the goal is to get coffee. No, no, it's fine.
The laser is charged and ready to shoot at me.
Oh,
One revenge. That's like mostly that's several. Expecting to spend like in a way that it makes
free that money for all the students. Or the other way around, just make it more.
So we said on Monday, like over. So in the morning, I was for a picture. In the morning, we do the honest stuff. I mean, also the people around. And then I would suggest, like after lunch, to have a longer seminar where the candidates
Check with the Hannes, but there is I guess.
There is also a guest.
It's not that we put everything.
But afternoon should be
Anything is only 27.
If you just run, just.
Have an interview on.
Oh, transients.
And then move things up and down.
So do you want, so I mean, I invite 5 candidates, so they will like.
We want them to give us percent.
Yeah, I think a minute.
Let's put
Nothing big, but
you can say 10 minutes.
already what 15.
No, it's okay. That's enough. And then another 15 minutes discussion.
Oh, okay. So now I thought like just short, but then you basically this is already when they also, so they don't, we don't have the office that they come to your office.
We could do that.
That's whatever you prefer.
I'm happy. Saying that maybe we. This means 1 hour and a half.
And I say, maybe you should talk some time that you have time to discuss further.
Yeah, I think just don't allocate too much because otherwise there is no time.
Yeah.
Just that find that number of hours per day. Then this is something that cannot be changed.
Okay.
Yeah, great. Okay, thanks.
I was trying to also you have the afternoon. Changed to this, right? Yeah, because.
Okay.
Yeah, I think today is pre dawn. Yeah. Yes.
Yeah, but it's like, noise. Actually, the seminar must be right after this section. I wrote down.
Like this is
Do you really imagine a book or other website?
I mean, even for the user, we'll have to pull it again. They have to add it after.
Like one of my future teams, that's why. The idea there was to have an extended system.
But like you don't have a choice.
This one? Gosh, what? It pulls from just type in git space. GIT. Oh, I a little bit, but I cannot focus on that because it changes.
I don't know if you've been doing this right.
I don't care. You can restore it. You do git restore and delete file. Okay. Go back to whatever.
There's less like
Oh, I'm now. Oh.
yeah. It's a short trip, right?
How long is Grace? That was like 3.5. Oh,
Masala is 3.5. It's taking like 4 hours.
okay.
The high-speed rail doesn't do much here. I think, oh. Yeah. Can't really complain when there are people from like Europe. Like Texas.
Oh wait, let's go forward one. Yeah.
This one. No, I typically
Right before.
before in like okay.
Or this slide.
This slide.
Yeah, like the exciton plot on the bottom.
Yes.
I'm just curious because the shape of the exciton looks like the shape of a polariton. So like, is this related or?
You mean this one? Oh, okay.
Yeah.
You because you're saying this one looks like a.
Yeah, like a blue.
Well, not really, because I think that's.
So it's just a variable?
Yeah, bilayer. Like look at the have those magic angles. You have a larger incremental size.
Right.
We're trying to push an expression for the electric function. We're
So this is for the plasmon, so it's slightly different. But for the epsilon, you use the Lorentz function. At that point here. Right, so this is epsilon omega equal to that thing.
We have several type of material. Even we can use array here, like
By omega t squared minus omega squared plus I omega.
Yeah. You didn't do that.
Right, so now this is a complex number. Right, so you can define the real part.
Yeah, it should be said, yeah.
And the imaginary part. Now the imaginary part is what gives you this peak. So if you just plot it, what gives you this, which is a Lorentzian, because the imaginary part of something like this is exactly the shape that you. So this is exactly the shape of what you would expect a Lorentzian to be. Right, so it's a peak centered at omega 0 and with a certain width, gamma squared. Right, so you just do the imaginary part of this and you get a Lorentzian kind of shape. So something that is proportional to this f here squared, and then omega minus omega 0 squared plus gamma squared. So that's peaked there with a width, which is this. And then the real part
JC
is this function here that has to go through 0 when this is peaked. And so that is just a characteristical shape of a real part of this object. It doesn't have to do with polariton itself. So it's important to get the surface polariton getting long, that this real part gets to be negative. And this real part gets to be negative, and the other material from the interface you're looking at. So let's say this one is epsilon 1.
I wanted to like head down.
This one is negative and this one is positive. Then you get the situation where kappa is real. So in this,
I think there's some very important here to go to this around.
It's real. If it's real, you get this exponentially down. But I feel like I want to.
No, but what is one? It could be this
the role of epsilon 2 being negative, the real part of epsilon 2 being negative. But it has nothing to do directly with the polaritonic expression. So this experience, two branches you see here, now this is the plasmon polariton, but they don't directly come from the epsilon. Also because you see that these two are split, right? The epsilon in the plot is going to the same asymptotes. These numbers are the same.
I think it's kind of like broad spectrum.
But I mean, it's a good point because it does look like that, right?
Yeah. Okay.
Also, it's a different, so another important thing. This is a frequency axis, whereas in the other cases, it's like momentum axis.
Yeah. Okay. Yeah. I was asking because in my project we use like perturbation theory and we plot these relationships over frequencies and
that actually I will show that because what you can also plot. So these plots that I've showed here are done in momentum, but you can also plot a similar Rabi splitting in detuning. Or as a function of, now I deleted it, but as a function of the cavity frequency. So let's say for a Pablo Perot,
Starting point is usually the summer when they
as a knob, and this L changes the
and then that'll
standing wave condition, right? Because this is because there's 1 over L, right? So if you tune L, you change this KZ, and KZ is what sets this dispersion. What sets the pair here? It sets this number. And so this gate Z fixes this number, and this comes from the rest. So omega is equal to the square root of k parallel square plus k Z. Right, so you fix this and you plot as a function of k parallel, you get a parabola. So that is a parabola when you square it. So I mean, if you like.
I have one last quick question. You showed also this plot with the beyond effective theory.
Yes.
Is that like, how do you know where the cutoff is? Is that explained in that theory?
Yeah, you don't really know the cutoff. You make a caveat that has that cutoff. So the other way. This thing is driving me crazy.
For like physics of this kind of stuff. Someone who already has a Nobel Prize.
Let me skip the animation, otherwise we stay here forever.
This guy should have.
Yeah, so doesn't want to be skipped. There. The idea here is that we pick a mirror such that reflectivity is cut at a certain frequency. So if you remember the gold Pablo Pro case, if you look at the reflectivity, the function of frequency here is around 3 dB for gold. It goes another case, blah, blah, another bit, and then it goes down. So now if I chose this number, so I chose the material such that this number was here instead. Say, I don't know, 1 eV, right? Then I will cut out all this. So the cavity is not really reflecting at that frequency. So I can make a cavity where only the first mode is high, but not the higher lying ones, right? So you can see that this mode function is very peaked here, but it's very small here. So, and that's the idea that then we can say, okay, we neglect that stuff because we would have to sum over all of them as well. And we only keep this. So it's more like you tune your cavity to make this mode. But in principle, if you have a cavity where you actually are building at these frequencies, that's the idea. And then the reason why it's 1 and 3 is because the mode 2 is the one with the node. This one, and our 2D material is placed in the middle. So the field here is 0. The couple are 1 and 5. The other ones.
What if in theory it's not like that?
Yeah, I mean, and eventually this is just a quantum oscillator with a volume which is cavity specific. So this volume depends on the geometry and the losses and whatever the cavity needs to be described from.
Okay, I'll think about that.
Yeah.
Thank you.
You're welcome.
Okay, so on the plot where you had it was like a 2D plot showing the Polaritons with the dispersion.
Oh, that was fast.
Right. Yeah, so here you said that if you plot the imaginary part, like this other half will be filled, right? And then you'll see the plasma, right?
Yeah, I mean, in this case, yeah, you probably see the plasma plot. This is a complex structure already, right?
Yeah.
Because you have gold, you have this guy, you have this one. This is a simple dielectric. So you could, in principle, start seeing the plasma polaritons of the gold, but yeah, maybe you see them in this. So I mean, because now it's cut, right?
So here you see the exciton polaritons.
So here,
this material
yeah,
is, and then you would see the plasma polaritons would be from
Yeah, but in that case, what we're interested in is the coupling of this one to the transverse mode, or that is bound by the mu.
Right.
So that's why, and I only focused on this.
Okay, that makes sense. So if you go, can you go back to more slides? Yeah, right here. Okay, so this is like what you see for right?
So it's a Drude model for gold and Lawrence. This is also sometimes called Lawrence.
Okay, yeah, that makes sense.
Yes, but the
Okay,
next one will look like that. I'll show you. The accident looks like that. Body. I don't know if you know about accidents.
Go back.
Look at the absorption from such an accident, you get the discrete states you get. And these discrete states, especially in two-dimensional materials, are very far down the gap. And besides the fact that this is hand drawn, but this one especially the lowest
Right.
and it's quite separate from this. So you can describe it as a Lorentzian mode. I mean, we don't do that, but that was just to show that that's actually what most of photonics does, and it's functioning all together.
Okay, that makes sense.
So that's the accident. The goal is I'll do the model. So you have the
Right. Yeah. Okay, that makes sense. I don't think I.
Yeah.
Oh, wait, no, that's yes.
You're welcome to ask.
I
also have.
It's a little bit more operated. Yes, but it's actually simpler than it looks. Let me go.
In the linear
Yeah, so but this is a little bit of a complication in the way it's written here, because so you see that first of all you already also don't have you don't even have a squared, you have AQ times AQ prime. Right, so there's two. It's like Q prime and Q. So you have photons in two different kinds. Because in principle, in a cavity, you might expand over modes which are not orthogonal.
You consider the cavity mode an order.
Yeah, but in most cases, you can do a rotation and you can find new modes which are orthogonal. Now, these are really just integrals between your matter mode. Now, these ones in general could be non-orthogonal when there is a cube, but in practice, they are orthonormal. So that means that this is a delta function, and this operator becomes the delta function in I and J and K2. So this operator becomes just that simple operator. And if you see if this Q dependency can be dropped, then it becomes sum over all possible electrons over the density operator, which gives you number of electrons. So in practice, this thing, in most cases, becomes the number of electrons times the A squared term.
So in this case, then it becomes the secure.
Yes. So there is no. So what I should add is that in this S, there is no operator inside. It's just an overlap between the two.
overlap of the between the because it's 5 level. And
so you can check in this paper how it's defined, but it's really like the overlap between different wave functions.
About the model profile you show, say that the higher wave region does not show much. Very low, similarly very low.
Yeah, so that's because this is a more realistic mirror. It's not just a perfect boundary condition. And like maybe you remember, I can go back, but you remember the plot for the reflectivity of the Fabre-Perot. It goes down.
Yeah,
it stops at 3V.
In a high frequency region, the mirror is looks transparent to the.
Yes, exactly. So that's the idea, is that we can design the mirror so that we exclude the other modes.
对，但是当然可能确实是做了一些
Yeah, because if based on the theoretical dispersion, the density of state actually goes even higher.
Also come all the things.
If you suppose omega equals to k
Friday.
Yeah, but the field fluctuation.
No, let's see, because maybe what I could do is right here is still hard. Not one. No, if we do it. No, but we
right picture like extends a broadband and we have some dispersive band given by the photon. Yeah, even photon case is also.
Yeah, so we could have right there.
Yeah, this one maybe. Schematic figure is also fine. Yeah, that one. So, but I think if you consider some physics material, Keystone or phonon also can have some dispersion by the wave vector. So
yeah, they do. The thing is that like
no, this you should not.
But
okay.
My question is, what kind of approximation or situation can this figure considering, and also what this has additional dispersion and additional wave vector dependent?
That's a good question. That's something that in the photonics field is
allows me to
also referred to as no localities. So I mean, I cheated a little bit by saying that the axon is flat. I mean, that's what it also shows in the schematic. But if you look at the excitonic dispersion, and I mean, the axon is a free factor, right? So it has to go as k squared, right? So it has to be proportional to k squared divided by 2. Right. But and the photon is dead. In a cavity goes as a that expression that I showed before, right? So omega, for example, in this case, this omega here, right? So the frequency of the first mode, so it would be pi over L plus k parallel squared. Let's say we're in 2D, so this is also here. Okay, so it's a 2dx. So these have dispersions, right? Now the thing is that this dispersion looks like this in the numbers, and the photon dispersion looks like this.
I see. Okay.
So then on this, in this range, this one is so flat that you can just say it's flat. So now the point is that if you can make gratings, for example, where you can start folding these regions, right? So that if this one is shifted down, now let's say that you could start the frequency such that the photon dispersion is down there. Then you can start probing the parabolicity. So it's really just a matter of like scale.
How much is classical, how much is quantum?
Right.
So
Basically, but if
I'm
you
not telling you that
consider
the
this kind of
answer
picture, basically only gamma point of the photon and gamma point external photon can couple with the
Essentially, yeah, it's a gamma point sort of coupling. And in fact, you can just use the gamma exciton wave functions to couple to photons, and then you get pretty much a good agreement with what is observed.
Okay, thank you.
So this instruction I think it currently explains the classical or FM
linear coupling. It's called
reach to several units, but how about
technically
level of molecular vibration?
Yeah, in that case, you would not couple to this excitons. You would couple.
In this case, for example, those chemical reaction rate, chemical infrared. So that in this case, it seems that the high frequency will not reach to the electron volt, so that you still have a very well defined K power.
Yeah, but it's just a matter of what excitation you're coupling. Right? So in the infrared case, the accidents are very ignorant about what's happening in low energy, right? So and it depends on what accidents, because some accidents,
but okay, this is
they are low energy as well. So you have materials with small gaps. And also we have some theory which will show that even if you have a very low energy, if you however have a strong coupling, you can have an compression on the accident as well. So that's sort of another way that they can couple. But in this resonance picture, the accidents usually are transparent to the IR. So you can couple them to ionic vibrations. But the ionic vibrations, they can be modeled exactly like a Lorentz. So that's like the physics I showed here is no different.
I raised this because this is value as it explains why the high frequency mode will
yes.
This would be vibration so challenge for high activities, the high frequency mode.
Oh, you're saying that like in the for low, yeah, you can have, but the problem there is that now we're considering epsilon to be in this case, although it's only like electronic transitions, right? Expression, but if you have different mirrors for IR like HPN, those are phonons that are making the modes, right? At some point, those phonons stop responding as well. That's why the properties of the polaritonic cavity changes as you move away from the harmonic resonance sort of HPN. So,
Markers have already been shown like so many times.
What do you have in mind as IR coverage? Okay. No, but the point is that like in mid IR, I mean, I don't know how gold works in mid IR. Probably fine, and then you can. I mean, you can have definitely multiple resonances, not just one. Right? So for sure, there are plenty of cases.
from
Our theory works more depth.
Okay,
So if you cannot exclude
those were energy
to carry all the
would you generate?
right. You can have them divided one by one.
Measure one or the other.
This modulator that it really goes into,
then they can also leak out because of, I mean, now in,
Take the calibration data.
I mean, this is
not a
a
due
very,
to diet system.
I mean, this is a true demo,
It
right?
is
But then
the
the most extremely
This is
cohering your response.
Parameters that you should be
Like when you go to I, you can see your like eye moment, eye spiral momentum. There are more things that you need to put into it. I couldn't model besides you.
certain parameters that you can get.
But the idea, I mean, the core points here are
but now we use them.
will stop reflecting and some come back. And extend to find the one.
You could try running on
And
forest.
anyway, that's not
Like, what is it?
but the most volume.
Some algorithms that are optimization depends on X. And you evaluate
No,
this.
point is that like a lot of these sort of interesting
Try to suggest the ground state.
the angle energy sector. This is one of the
Okay. And then the edge is
But you can solve variable harmonics.
Of course, nowadays was everything extremely simple.
Really this physics of two oscillators.
But at least you get to know that one of the things that you see is not formulated the way you did it. Never. Because you get separations, but give you a feeling of
So when you first start
there are many things that you could eventually do.
Yeah, they always take.
Maybe that.
I think your former group member also related to Marvel's paper, so you know
The last part is
understand that. Michael and I compare this paper.
To the Marco? No, I don't know. I only know Marco because he told me that. And I'm trying to get
They're all named after
Carolina,
like certain.
which is the collaborator of Marco, to come to have.
That's
I would assume there's enough Cairo, but I don't think. I think when you make the policy, Egypt is one.
But we should discuss. I'm not.
this is
I don't know who go to you, but
this is treatment of the cavity.
but in our case,
Perfect.
Yeah.
And then this is something like Google.
there is nothing contradiction.
There is a question, in all of this on localities. One, what constitutes?
Yeah, so basically what you're asking, get close to
I
absorb
think the devices that are trying to run on.
It's a probably dependent on what you're trying to do, but as long as you make sure that the weight that it carries is consistent with, I mean, so it does a function some number, right? Effectively.
That's one of the main.
Because I mean, I guess if you wanted to approximate a direction,
We have few of the devices that modify.
you would want that assuming that there's no resonance effect on this, you would want that the area under the the integral of that.
I'm not sure if all.
At least I would say that then it's consistent in the sense that it carries the right amount of states.
Okay, but it would be better we need a readout.
Yeah, that or approximated convention. Maybe you see what I mean? Because that's a function of convention. And you can see is there an effect on this broadening? Probably it's not massive because it compares sort of right?
Events count.
But just as a check, and then you could say maybe before you do try to do like the weird shape, just try to take the suitcase buttons and then just see what.
I don't.
So
Because I mean I think it was the plan.
Very, very good.
Because then that will give you an idea what that is.
I hope I did not promise them too much that
Arun is the previous.
But I think I think more along the lines of.
Okay, then it's, no, that's it's important. Then he's coming from the
11,
11.
No, but more the way you interpret the not so much the other thing. I think we were pretty.
but actually that was I don't know.
We had a lot of discussion. I think we showed him a lot of things.
Why the upper Polaritons is
Electric
I mean, because you don't see it.
So I
No, but
Sure, but,
I know that. No, the point is that he is laughing with a lot of people.
It has been a common.
It's a common.
But he
No, because
interprets
if you do
me.
this standard phonon, and dynamic
That was
phonon,
Yeah, those are the general.
they are the
Yes, yes.
I mean, there is no way for
I mean, no idea.
right or anyone else.
These questions is super. Yeah, it went.
It has to go through the
But if I would use
but
this
the lower is the
elevator
one that gets.
idea, so
Yeah,
the usually
the
ground
the lower is the one that
that's
gets-
the width of the direction, that's anything package. Because your model of the circuit is
So
on its
why
own
should we
perfect.
do it?
So maybe the very fine
Of course,
details.
like 2 equals 0 is tricky because what is the low and what is the
Well,
Q?
if they do, it's interesting.
I don't
I
think
think
that's,
that's why more than.
The main thing that matters essentially is the reflection. Because of the function that we're integrating over.
Solve the problem or doesn't change. So in the limit of omega equals 0.
Yes.
But it's not a problem.
But you are
It's
right,
not a-
it says it's one of
There's
those.
the lower one that's clear, that it goes to the TO.
Yeah.
But this, yeah, maybe it's.
Because so what enters is
So you were
and if you are a large X on a small frequency.
surface plasma, there's always TM.
For the trivial isotropic materials. As far as I
I
know.
think it depends if the extremes of the dispersion, I think it's very high.
Because of the losses or?
I mean,
a very high Q.
dispersion, you know.
Yeah, but if I were you, I would
So
literally.
what I meant is that it's a TM like mode, but it doesn't mean
Right,
that
and
it's
then-
longitudinal transfer.
It's also, that gives you a nice expression, right? Because it basically
Because you have
gives
two
you.
components, so you always have EZ, which is out of plane, and EX, right? So then that means that if you have an EX along the propagation,
Okay,
and then
not exactly, this becomes a
X
test.
transfer.
This is always,
That's kind of, then you have something that's directed.
Yeah, because
Yeah,
Find it
it's-
always in
it
the-
is,
we have always
Broadening this
discussed
out.
general
and it's very, I mean, that's
Probably
actually
more
something that is
interesting
very important when we do work on.
Like, you know,
Right,
this
because it
exact
gets more and
shape
more
of the
longitude,
thing,
like
and then
here,
there's
along the
like
propagation.
how high can
I
it
just reiterate.
then have the surface.
I got to today.
Polariton.
We try to organize something for Monday.
That's one case.
The number, yeah, so it's not working.
I'll just tell
Something
them
that's a little bit more
10,
general.
15 minutes.
So grunge in and
No.
Oh,
This is,
so
that-
that's-
that-
that's urban
from the
blast.
growth shit.
but that also doesn't work, to be honest.
Because it's like this 6. I would try the other. Try the. Because I think it's more interesting, we can always, you know.
So just in case it was not
this
clear,
corresponds to being this.
you are supposed to do the exercise now for the next 10, 15 minutes, okay? And then please do it in groups, because I'll ask someone from the group to say what they have observed.
Yeah. Yes.
The first one. I think the other one is a little bit more advanced.
That's the number of layers.
Yeah, maybe it's yes, that's right. So I think just
Yeah, I tried to send it a knowing that I didn't let me attach it. It's more than
Oh, yeah.
Okay, try now.
No,
Okay.
Yeah, they're in
Oh, sure. Yeah, sure.
How the function works.
Here it seems like
Right.
yeah, the summation makes as small as possible. Yeah. Is that the reason?
I think so, yeah. Typically, it's much more expensive.
Yeah.
Try, let's go.
Yeah.
Yeah. That's a commitment. This afternoon is just one more talk about imagery. No, that's it. Only after 3. So you can get some.
I mean, that's
No, that's just meeting. But even at 2 hours. You have a meeting. So it's more busy now that Antoine is back. No. Yeah, it's independent environment.
So we just describe it in one. Take one example. But already from today is not. And the polarization of the electromagnetic field.
Okay. All right, this was the cross check. A hat.
I don't know, maybe it could be useful. It's and then you apply. And then you yeah, that was.
So just a gentle reminder to talk to each other, because I will ask questions per group, and I didn't hear much talking. So you have 5 minutes to discuss and come up with one comment/question per group. So up to you. Either you do it now or you improvise.
Use these functions.
Okay, so they have some
We just give this some random.
What dimensions they should have.
Matter Hamilton should be a diagonal matrix with energy gap delta. Which is what this is. I don't know what this is. second matrix. This is just the first block, just with a naught equals to 0 and omega equals to 0.
Like here we just model it.
Oh, but you can input it.
So they didn't specify what the prediction is.
The matter part will just be diagonal, where delta is the difference in diagonals. I think that's the white map. I think the matter Hamiltonian is this part.
Which would happen. It did not work.
You're right. It's
Must have some different dimension.
So it's
like what we see in this whole thing is what we see in the code will do that for us and build each is like a shift.
For this Solomon's potential. This is just like the most sensible thing to
the first argument after Hamiltonian.
Like write out the x squared and x to the fourth terms in terms of the ladder operators. Construct the phonon Hamiltonian that way.
So I think if you just do the gap, it's basically what we have, right? But then how is the gap?
Or is it like a more straightforward way to do it?
Delta is the gap. Yeah, easier to write into some scalars. That's not a parameter.
Yeah.
Of the dimension of the number of photons we have.
Yeah.
I guess it's
And each one.
did it say so, or E matrix is really just the? Okay, so what is n? So matter basis.
No.
It's the photons.
Yeah, I think.
So we are.
For setting up the diagonal, I assumed that we would have.
Matter basis, usually IH or DX. Yes. So how do we pass?
Yeah, some previous calculation, I guess.
Should be integrated again, right? Right, we would need to come up with matrix elements.
We're not multiplying it by.
No, so all this.
Yeah. How the momentum operation is. I think the dimension should be this.
Are you doing it?
Yeah, he said it should be
What? Sigma X, the Pauli matrix? Excited. Why is that?
Yeah, I think because.
I'm assuming current.
Yeah, okay.
It's like I don't know anything about the character of the ground state and excited states.
I don't, otherwise it's just dense, I guess.
Dense?
Yeah.
On what?
So like all these.
I mean, I just put one.
Okay.
I think these two are not so. I mean, that is zero. I think. I don't know what realistic. I don't know what's realistic, so I just put one. Wondering about the
question I asked. Okay. Yeah. vector potential amplitude. One. See what happens. Oh, I didn't choose this.
It's just, I mean, there has to be, if you want to build this matter part, I guess this is the matter. What basis are you using for the phonon Hamiltonian versus electronic excited state? And so you need the vector forms. I'm just guessing that the vector forms. I'm just guessing that the ground state vector form is 1, 0, 0. Okay. Excited state.
Oh yeah. Oh wait. Before we do that,
It has to be 6 by 6 because I'm
I can't do it. So it should be.
So let's print it and see what we get. Oh wait, so
Hard to tell. I ideally have to create this thing using the arguments and comparing it.
For sure, there's 0 choice. Let's see if that's correct. So you need a delta. You get delta here. But you also get delta here. So it's probably not correct. Because I think if you just take the matter part,
It's maybe related with how you create an excited state. Yeah, because delta over 2 is because of your gap is half. Right, so that's why it only shows up as half of half, I guess.
yeah. So then how do I create the first 6 units? Yes,
where I'm screwed, I guess it's -1.
Buried into A naught.
Yeah. Maybe like a fracture movement drive, like okay. So these are the right dimensions. So okay. So very.
yeah, and then we can define
An array of numbers and an array of.
Fascinating. I suppose if you wanted to pass in omega d computing alpha omega d.
Epsilon.
12. It's 12. I don't know. Wait, what happens if we? I'm just like curious, like what happens if we
Photons to 2. I guess you should.
Pass in omega d as our parameter and then solve for A naught.
don't necessarily know.
Where's that?
Yes.
Oh, you do. It's a parameter. How did you what formula did you have for the?
Oh yeah, but there's a free parameter here, right? We would either pass this in or pass this whole thing.
Oh, okay. 2 by 2, right?
Yeah, the tensor product.
That's what I thought.
Okay, this makes sense, that would give us the.
Then I
Yeah.
It's kind of a dressed frequency parameter. This is the Fock space. Light matter coupling is lamp.
Yeah.
That's this thing. This one. It's the inversion. When we match this,
Maybe I have.
You have to put it to 3.
Actually, it's fine. You can give it.
They're related.
Oh, okay.
I found some.
Our free parameters.
Yeah, it's your one.
All right. So I think then you have to pass in mass.
I guess would make sense.
Squared over figure space. All right.
Very easy.
Yeah, I tried to wear it and it's just maybe I need the coupling.
Okay, so we get these three.
Yes.
Oh, that's the square of the thing. All right.
Yes.
Looks good.
Looks like something.
So right now we get three of the same. Yeah. Which makes me, well, I think that's probably original.
Okay, so it's a shame that I have to interrupt you because finally it's nice to hear your voices talking to each other. But I will do as I promised. So I'll ask each group to comment or ask questions. So maybe we can start from my second favorite number, which is number 3. The first favorite number is not part of the groups. So where is group number 3? Well, I'll find out. So you can hide it, but as much as you want, but eventually I'll find out.
We're group 3, but like there's only 2 of us and it's all over the place.
Well, that's enough to have one comment. So the whole line is group.
No.
No, just
Three.
me
I
and
don't think we are sitting according to the group numbers.
Okay. Reason being, you can, but maybe we can help for the next lectures. You still have to come up with one comment or question, either of you.
So looking at this building Hamiltonian part, I'm confused with how to.
So the part below?
Yeah, the first function.
Tell me when to stop.
The PMAT. So I'm thinking it's an operator, so it should be something like finite differences. But
this one.
Yeah.
Yes.
I don't know what to supply, what to give it as the PMAT. PMAT is the momentum operator in the matter basis.
The PMAT is the momentum operator. Yes.
Right. So that would be for derivative finite differences or something.
That's a good point. It could be finite difference, right? And actually, in the next part of the exercise, it will be finite difference. But for this exercise, you have 2 electronic states, right? So that means that you can define a matrix element and give it a value. and then it becomes one value in the matrix, right? So in the essentially, if you open this hint, this is the matrix that you have to solve associated with the Hamiltonian above, right? So this is the Hamiltonian you have. The ansatz here is that you solve on this system where you have one ground state and one excited state. That's it. So then you can expand or project this Hamiltonian onto this reduced Hilbert space. And then you have on the diagonal the energy of the photon field plus the ground state energy of the electrons, which is 0 in this case. Then you have the excited state energy, which is this delta, plus the 0-point motion of the photon. And then again, you have the same for the case where you have one photon. In this case, you add one full cavity photon energy. And that's the diagonal part. That's uncoupled. So if you just add this, you would just see uncoupled systems. But then the P matrix is exactly what defines this block here. And you can see that it's a number, 80, which defines the coupling strength. And P, so this is this defines the volume strength, so the cavity mode strength. So that is related to how much the cavity is confining. And then the P, which you're saying, which you just mentioned, here it appears as a number that you have to provide. And this is a matrix element between the ground state and the excited state, and the matrix element is of the P operator, which you could do in finite differences. And in the second part of the exercise, you will do that way. Yeah?
Yeah.
Good. So now group either a spontaneous question or I decided a group number. So, okay.
I have a, sorry.
Yeah, you can go ahead.
No, I was just wondering that like all of this assumes that the electron states are much localized within the cavity, right? But like let us say that I have an exciton that's in the 2D material that can roam around everywhere, and the cavity itself is bounded by that same boundary. Does that change?
Yeah, so excitons usually, it could change if the cavity mode volume is much smaller than the exciton radius.
I mean, that I have this two mirror system, but I have HT micropillar, and I have a 2D materials which shares the same boundary as the cavity.
Yes.
Then does that? Yeah, that was kind of what I was wondering. But then the electronic states shares the same boundary as the photonic operators.
Right. The question is if those boundaries are small enough to affect the quantum properties of the excitation. Now, usually your micropillars, I would imagine they're on the order of a few hundreds of nanometers. And that is way larger than any excitonic wave function. So the exciton doesn't really care about being in a confined quantum environment. Now, if you take that to a dot and you make it very small, like now on the order of tens of nanometers, then the exciton could care.
No, I was more thinking of a quantum world structure that can be extended to that 100 nanometers.
Yeah. Then in that case, this simple theory should be revisited. Yes. Lucas, you had
so in this case, you're projecting essentially a continuous meta theory onto a two-level subspace, right?
Exactly.
This explicitly breaks gauge invariance. Is this like for realistic systems, is this a good approximation?
So because this model is meant to provide the Polaritonic dispersion, the linear response, yes, it's good. So you don't need to care too much about gauge invariance in that case. If you want to change ground state properties, the single mode approximation could be tricky. But in this case, the goal of this exercise is to show that you can use a quantum description where you have a very simple system, right? So you don't even have to solve Maxwell equations. You have one excitation for the matter and one photon mode. And then these are two bosons, essentially. You couple them, their dispersion intersects, and you get a Rabi splitting. So more, for example, from group 5. Where is group 5? Okay, you ready? You want to share something? Okay, that's fair. Group 5 has been already represented. So group, remind me the group number.
I wasn't 5, but I think we may have scrambled the numbers.
Okay, fair enough.
I was going to ask, in our representation of the momentum operator in the matter, ground state, and excited state, why do we assume the diagonal terms are 0? I wouldn't know that without symmetry representations or something.
Yeah, so I mean, here the assumption is that, for example, in the ground state, you have no currents, right? So if you take the expectation value of the momentum operator, where this momentum operator, I briefly showed it before, is the total momentum operator. So you would not expect to have a ground state with an inherent current, right? Then for the excited state, these kind of excitations, which are like zero momentum excitations for the exciton, you also would not expect to carry currents. So that's the assumption there. But in principle, if you expanded the full theory and the full Hamiltonian, you should also take the diagonal part of the P operator.
Okay.
So the idea is that a ground state should not have any current. So you cannot have any diagonal term that goes with the momentum because the total momentum expectation value is 0.
All right.
And same for a neutral excitation at Q equals 0. Yes?
How do you see the Rabi splitting with the results of this exercise?
So did any of you get to the results? Raise your hands. Only one?
I was getting some help from him.
So then you're at least 2.
Yeah, I have to do analyzation. I haven't done the plot yet.
Okay. So also one thing that I should mention, in the next days where you have the full afternoon for tutorials, you will have more time to go back to this. And you can go back to this in the next weeks. And you're very welcome to ask more questions later. I mean, the program is a bit tight, but I believe that through these notebooks, we can get some of the notions a little bit more embedded in your head. So the point here is that you can set up the Hamiltonian. And to do that, you define first the matter Hamiltonian. And this is simply these two excitations. So you have the ground state and the excited state. Then you define now an array for the cavity frequency. So it's just like checking how the dispersion relation, in this case, the eigenvalues of this Hamiltonian, change as a function of the cavity frequency energy. And then you use the help function that is provided above, which if you want, you can take a look at, and some of you did, to build this polaritonic Hamiltonian. And the polaritonic Hamiltonian is nothing else than this guy here. So this function is just putting together this matrix. You could put it together as you like. So you put this matrix together and you diagonalize it. That's it. And then the task of the exercise is to plot the eigenvalues as a function of this cavity frequency. So this is cavity frequency in the units, arbitrary units used to define the model. And then you will see the following states. So the gray lines are the lines for the uncoupled system. So you have one line per photon mode, including the 0, 1, the vacuum. So that's this one. And also the vacuum has a dispersion because you have the diamagnetic term, which is not necessarily linear. And then you see that if you were uncoupled, you would also have the transition energy for the first excitation and the first and only excitation you have in the matter. And this will be a flat line here. Okay? But now when you couple two photons, you see that this flat line actually gets split into two. And this splitting here, now this is small, in this case, is the Rabi splitting. Okay? And you have this splitting over different photonic branches. And I'm not sure if this is going to work live. Let's see. If I change this one, which is setting the coupling strength to say 5. Let's see how many errors do I. Oh. Then I need to start it from the beginning. Then you see this splitting here is getting bigger, right? So by changing the 8-0, you're getting a bigger Rabi splitting.
Why is it that the splitting is largest near the cavity frequency and smaller everywhere else?
Yeah, that's because, I mean, if you just take a simple 2x2 matrix, you could see it right away. When you hybridize two states, you want them to be close in energy. So if you have a matrix like this, let's say epsilon1, epsilon2, and then a coupling term, C. Right, so this is your Hamiltonian. This could be, for example, the Hamiltonian representing two discrete levels in two molecules. So this is epsilon1, for example, and this is epsilon2. And this coupling makes these two levels talk to each other. Now, from chemistry, you know that if you want to make hybridized orbitals between these two levels, you can usually construct a drawing like this, right? But what is this drawing telling you? Actually, this drawing is telling you that if you made these two orbitals talk to each other, you get two different levels, two new levels, molecular levels, right? Whose splitting depends on this coupling, but it also depends on how these levels are aligned, right? So if I put these two levels completely misaligned, so one level is here and one is here. So this is the typical drawings you might do in chemistry. Then even if the C is as big as in this case, the hybridization will lead to orbitals which are much closer in energy to the original two orbitals. Right? And actually, the way to see this is that you can diagonalize this matrix, and then you will see that based on the detuning between epsilon1 and epsilon2, this splitting becomes larger or smaller. So essentially, you diagonalize this matrix, and then you get the eigenvalues. So from here to diagonalize it, you have to take the determinant of this matrix here, right? Yeah. You take the determinant of this, and you get lambda minus epsilon1 times lambda minus epsilon2. That doesn't work. Minus C squared. And this you have to set to 0. And if you look for lambda, you will see how this can depend on the difference of epsilon1 minus epsilon2. And it will be larger when the two are the same. Because you get two branches from this. No, it's a quadratic equation. So you get a lambda square, you have two solutions. And the two solutions will be exactly this one and this one. Yeah. Is it clear to everybody? Any last comment on this? You'll have more time to do the exercise, but. No? Okay, I will not enforce you any further comment. So let's go back to the presentation. Right. So the goal of the exercise was really just to set up this simple model. So again, we have seen how to get the full theory and how to include losses and everything, but we need to get the basics right. No, so we need to be able to reproduce the linear response. Okay. So now what you have done here is simply looking at the spectrum you get from mixing a bosonic mode with an excitation in matter, in that case an exciton, okay? There is still a step to do to go from this one to a linear response, but in the same spirit as you get linear responses from condensed matter systems, a linear response would just be a function that has to click or give you a resonance when you hit a resonance of the material. So it's got to be a response. Yeah, it's got to be a function that whenever you hit one of these energies, will click and explode. So give you a resonance, right? So in fact, in the other exercise, which you're not supposed to do now, but you're very welcome to look at in the next days/weeks, you can build a response function out of these quantities. So essentially, you just sum over all the different poles for a given cavity frequencies with a certain matrix element that tells you how much the system is able to respond to now a probe perturbation, which has nothing to do with the cavity photons necessarily. Okay, but then you cannot expect anything else than seeing lines that disperse the same way that these lines do, because the response function is just probing the resonances of your system. Okay, so this is exactly the background picture that allows you to have this polaritonic Rabi splitting. Okay, but fine, that's a linear response. We didn't need to do this diagonalization. Although, I mean, it's much simpler to diagonalize a 4x4 matrix than solving Maxwell equations, I would argue. Okay, so now the point is that I mentioned that one reason why we might want to use a quantum picture is to interpret nonlinearities and strong coupling effect in a different way, or maybe more convenient way. And you have seen from June, like categorization of coupling types in cavity matter systems. And there is a number of nomenclature. So there is a large nomenclature to describe these cavity matter systems. But I think the relevant terms can be boiled down to these four. So you have the regime in where the light matter system, the light and the matter system are coupled in a weak way and in a strong way. And this regime is defined in terms of the Rabi splitting and the width of the peaks that you would have associated with these resonances. Okay, so if you do the response function on this calculation on these resonances, you will also get a width, not just like the trace of the maximum. And if this width, which tells you about the losses of these branches, is much smaller, or it's smaller than in this case, than the Rabi splitting, which is quantified by this G, then you're in weak coupling. So the G divided by their width defines a weak, and if that is smaller than 1, defines the weak coupling. And in this weak coupling regime, what you can expect at most is enhancing, for example, your transitions. So you can get, for example, more light out from a photoluminescent system. Yes?
So why would I see a broadened spectrum in the model we have been looking at?
No, in the model you will not see it. But if you calculate it for a real system or you do the experiment, you would have the losses inherent to the both material and mirrors, right? That's also important. So now both losses chip in. And yes, there it is. And then if this one instead is bigger than 1, then you're in strong coupling. Okay, and in strong coupling, the effect that you would see is the appearance, a clear appearance in the experiment of the Rabi splitting. But you have seen already this from June. What the Rabi splitting implies in real time is Rabi oscillations. Okay, so if you look at the electronic population as a function of time after you have excited this polariton, you will see that this is oscillating in time with a period which is directly related to the Rabi frequency. And this oscillation is really telling you that the matter system is exchanging energy with the photonic one. Okay? And in fact, the fact that you have G divided by omega bigger than 1, it means that you can exchange energy between the two systems within one Rabi frequency. That's the definition of strong coupling. And then you have a completely different regime where instead you don't compare G anymore to the losses, but you compare G to the frequency of the excitation you're trying to change. And in that case, if this ratio is smaller than 1, you're in what's called ultra strong coupling. And if it's bigger than 1, then you're in a situation where you have this deep strong coupling. And in that case, you need to be careful and include all the modes that you can, because nonlinear effects and non-perturbative effects can be important. And June has shown quite a few examples on this. Okay, so please, you can go back and look at those slides again. Now, to connect again to the model that you've just solved and to make it a little bit more realistic, I wanted to just show you an example of one of the first works we have done in this cavity, ab initio cavity QED business, which is related to excidents, specifically excidents in 2D materials. So the idea here is that you take a two-dimensional material. If you have never heard about these materials, it doesn't matter. It's just a material which is very flat. And then you embed it into an optical cavity. In this case, a simple Fabry-Perot resonator. Now, why is this interesting? Well, because these 2D materials can hold something called excitons. So maybe most of you know what an exciton is, but it's probably worth reminding you. So take a semiconductor. So that's usually where the excitons feature appear. And then in a semiconductor, you would have, in the minimal description, a valence band and a conduction band. And the valence band is full of electrons. So this is the simple textbook picture. Here is also a simple picture where you have a band dispersion. But this bunch of states are full. Now you come with a photon, and then you can excite an electron-hole pair. So you take an electron from here and you put it in the conduction band, and then you create an electron and you leave a hole behind. Fine. But then you would guess that the energy required to do this transition is proportional to the gap. So you would argue that if you do an absorption experiment, the absorption will start only if this energy of the gap is available. But if you do that, in reality, it's not like that. And in fact, especially in two-dimensional materials, you start getting in-gap states that should not be allowed according to this picture. Okay, and these in-gap states are very isolated. Okay, and this actually look pretty much like the Lorentzian shapes that you have seen before. So that's why Lorentzians are actually pretty useful, because you can model these absorption peaks pretty much essentially with one or a few Lorentzians. Okay, so why does this happen? Well, the reason why it happens is because if you create an electron and a hole pair, then you expect these two particles to attract each other, because they're nothing else than an hydrogen atom. Now there is a very a much more rigorous way to prove this model, the emergence of this model, so it can be proven from ab initio. Again, it's a useful model, very useful model. In fact, most of the excitonic calculations can be done in this picture. And now it's really like an hydrogen problem. So you have the kinetic energy, which in 2D materials has to be in 2D. And now the kinetic energy depends on the effective mass of the exciton. And then you have a potential. Now, if the electron and the whole pair were in free space, this potential would be 1/r. But because these two particles are embedded in the rest of the material, then you need to take into account the screening of the material. Okay, but those are details. Essentially, this is really the equation of an hydrogen atom. And if you solve the equation of an hydrogen atom, this is essentially what I showed, you end up with discrete states, right? And these discrete states will be below the continuum. So now these discrete states can actually be accessed from the photonic excitation. So an exciton is nothing else than an excitation to these discrete states that come from the fact that the electron and the whole pair interact with each other. For example, in this notebook 8, which we call Deluxe, which you can do later at home, you can actually see how you can implement this Montoya model. And this is, for example, a set of states that you get from the parameters that are set for a typical two-dimensional material. And then if you plot one of them, you just get something which looks like an hydrogen atom in 2D. This is an excited state with n equal 4, for example, where you have multiple nodes. If you plotted the lowest one, you will get a spherical symmetric state. So nothing surprising. So, but the point here is the following, and I just want to show why, in fact, in a cavity, we might need a quantum treatment. So if you now take a material and you do an absorption experiment, similar to the sketch I showed you before, without coupling to any cavity. So this axis here is the cavity frequency axis, but in this case, we assume that this mode volume of the cavity is infinite, so that the H0 is 0. So there is no coupling. Then nothing should depend on the cavity frequency. So this cavity frequency is something that you can control by changing the length, the distance between the mirrors. So you just get the peaks you will get in free space. And it happens that for 2D materials, you only get peaks called S, which goes for spherical symmetric. So just the spherical symmetric orbitals of your hydrogen atom. Okay, so this is a real system. Nothing happens if you don't couple it to the cavity. Now you couple it to the cavity in a not too strong way, then you get Rabi physics. So you get that according to the brightness or the oscillator strength of each of these peaks, you get a bigger or smaller Rabi splitting. Also nothing special, right? Again, in classical physics, you can put one Lorentzian for each of these transitions, you get exactly the same. But the nice thing comes if you are in a much stronger coupling regime, because what happens now is that, first of all, the Rabi splitting are ginormous, right? So you start pushing bands across each other. On top of that, you start activating transitions here and here, which were not there before. And this is really because of virtual processes that happen thanks to the coupling of the excitonic fine structure to the virtual accessible states of the photons. So this is really an example of nonlinearities. And essentially what we found out, because we could diagonalize this problem exactly as you just did, but just increasing the number of electronic states. And in fact, you can do that in the notebook Deluxe. You can use the model and exactly get the same physics here. And then what we found out is that through virtual excitations, for example, connecting the 1s state to a p state in the the photon number 1 Hilbert space sector, and then going back to a d state in the 0 photon sector, you could mix s states with d-like states. So now these d-like states are the ones you would expect for an hydrogen atom, but they are dark usually, so you cannot excite them because of symmetry. The dipole matrix element just doesn't work. But because you're coupling the S with a P and then back to a D, those transitions are allowed. And then you can actually brighten this transition up and see it in a response experiment in strong coupling. So now the point is that the experiment here, the probe that would give you this response is perturbative, just the probe, but the photons in the cavity are strongly coupled to the exciton, okay? So you can include, you can see in linear spectroscopy the effect of nonlinearities of the strong couplings. Yes?
Why is it okay to like disregard the center of mass motion of the exciton here?
Yeah.
My intuition tells me that that should increase the coupling strength effectively, right?
It does, and we also have some work on that. But the point here is that we're using unstructured cavities. So like in the example before, if you just look at the dispersion of a Fabry-Perot and compare it to the dispersion of a typical exciton with a typical effective mass, and you plot them against each other, the Fabry-Perot cavity has a parabolic dispersion, but it's very steep. So this is the energy of a Fabry-Perot. And if you plot on the same plot the energy of an exciton, so this is not necessarily at zero axis, it would look like this. This is something that goes, because it's a free particle, into first approximation, it's something that goes as k squared divided by 2 times the excitonic effective mass. So this mass here is much bigger than this curvature here for the photonic part. So what you're probing with the photons, if you do not do any structuring of the cavity, is this energy. Is this region of the momentum space. So it looks like flat. So you don't need to take care of that. So any questions on this? Is it surprising that, yeah, please?
Out of curiosity, have there been some studies that are like purely ab initio, where people have tried to model exciton, strong exciton photon coupling and see things like this?
So this is ab initio.
Oh, really?
Or you mean like experiments? In experiments, I haven't seen anything showing this yet. So, but this is done ab initio with the caveat that the cavity mode is set as a parameter.
Okay.
So, and that we set such that we could reproduce the Rabi splitting that have been observed for this particular excitation, which is the strongest one in experiments. But they didn't look at higher lying excitations in that experiment. Yes?
A single mode cavity in this case.
It's again a single effective mode cavity. Yes.
And the argument here is essentially that you have the resonant kind of coupling to your meta system, right?
Yes, I mean, but the nice thing is, so the thing is that the cavity is resonant. Say we have different cavity energies, right? So for different values, you have different resonances with different peaks. For example, if you around this region, you're resonant with the 1s state, right? But this gives you the standard Rabi splitting picture. But the point is that if you do a transition from this state up and then down, there is no necessary resonant condition, right? So you can have this virtual excitation even without resonances and still have this mixing effect.
So intuitively, I could think about these feature scaling as interaction squared.
Exactly. So this goes as the square. So it's a nonlinear effect. Okay. So that's another nice way to see something that maybe one could have seen in nonlinear optics with defining nonlinear terms for the Maxwell equations. Okay, so, but that was just to back up my claim in the previous slide that quantum could be useful for nonlinearities. But now there is another deeper thing that becomes quite apparent if you just do simple perturbative arguments. So again, consider the the most interesting part of the light-matter interaction. That's the paramagnetic term. Okay, so you have the total momentum times this bosonic effective degrees of freedom. Nothing special. And then let's do perturbation theory. Okay, so how do you do perturbation theory? Well, you take, for example, to first order, the guess of your wave function to be a tensor product of the unperturbed wave functions. So that's where you would start a perturbation theory for a combined light matter system. So you have the electronic ground state and the zero photon state. Okay, fine. You do first order perturbation theory on the energy, you get 0. Why? Well, you have here, for example, A dagger plus A. Whenever you try to make a bracket of that with 0, you get 0. No? Okay, good. That's fine. You do second order. Now you have to sum over excited states. So the excited states also should be the unperturbed ones. But in that case, you also have not only the 0 sector, but also excited photon sectors. So you have the photon number 1, 2, 3, and so on. So those, especially the ones with m equal 1, will click with the ground state 0 photon sector. So this sum is not necessarily 0. And in fact, it's not 0. And the change in energy goes as H0 squared. Fine. So the change in energy in perturbation theory is a second order change. Now, if you do the same thing with the wave function, it's enough to be first order. And you do get a change because you get exactly the same terms here, right? So, I mean, this is the matrix element you have to evaluate in wave function perturbation theory. But then guess what? This change scales with H0. So we are in this situation where for this specific, for this QED problem, the scaling of the wave function with the cavity mode volume is of order 1, while the energy is of order 2. Okay, so this really calls for something that is beyond perturbation theory, because if we don't account for the changes in the wave function, and we try to just look at the changes in the energy, then we're doing an error which is bigger than what we're trying to calculate. So that's why this Polaritonic picture is not necessarily correct, especially when looking at the ground state properties, right? Because for excited states, you could get Rabi splitting, and this would not necessarily be 0, right? Because you can get transitions from ground state to first excited state with 1 photon. But in the ground state, this has to be 0. So this is the first order you need to take into account. So you need to change the wave function. And the only way you can change a wave function is through an ab initio method. You can do no model. I mean, you can model a wave function, but still, you're trying to model the microscopic ingredients of your system. Okay? So, and I think this will be the main motivation to what you will see, I think, from tomorrow onwards, because it's lunchtime. And just quickly, I want to at least tell you the physics behind the example that you're very welcome to solve in the next days and ask us about, which is the one of the first material platforms that we used to show that the cavity could do something to a material. So this is the story of STO. This STO is a perovskite material. And it's a material whose ground state properties are dominated by a specific phonon mode, which is called ferroelectric soft phonon mode. Okay? And this phonon mode is associated with something called ferroelectric transition in principle. I'll tell you a bit more about that in 1 second. So if you look at the phase diagram of this material as a function of temperature and strain as a different number of phases. So at room temperature, this material has a cubic phase. If you cool it down, it becomes tetragonal. And if you look at the type of ferroelectricity that this material displays. At 0 temperature, without any strain, the material is a paraelectric. So meaning that there is no polarization. There is no macroscopic field associated to this material. Okay. Now, the point is that if you strain it a little bit, so you see maybe it's a little faint here, there is a little dome that arises that if you strain the material, you can make it ferroelectric. Okay, so it's in principle a material that is very labile to perturbations. So the idea was like, okay, can we promote this transition by coupling the material to a cavity? And this was a material that was investigated already in a dynamical way by using strong laser pulses to switch this ferroelectricity on and off. Then, okay, we set up a low energy Hamiltonian, which is actually not that different from what you have seen so far, besides the fact that the matter part is explicit now, and it's not related to electrons, but it's related to phonons. So you have the first part, which is a combination of two vibrational modes. You have the ferroelectric mode, and the ferroelectric mode is actually quite nice. So you have a titanium atom, the blue one, which is moving with respect to an oxygen plane, the red ones. Okay, so because this system is ionic, right? Then whenever the displacement of the positive atom and the negative with respect to the negative one happen, you generate an oscillating dipole. Okay, so this is the target that we want to hit with our cavity. This other mode is not that relevant for the sake of the story, but it's the mode that is associated with the elongation of the cell in the same direction where the ferroelectric mode is displaced. It doesn't matter. What matters is that if you look at the potential energy surface describing the system in these two coordinates, you have a double well-like surface. Okay, so this is the ferroelectric soft mode coordinate, and this is the displacement of this lattice here. So this might be tricky to see here. Maybe it's clearer from this top plot. But if you take a cut of this curve here, you get a double well potential. So, and this double well potential is a very shallow double well potential. And this is crucial because if you just did classical theory for this phononic system, you would expect that the lower energy state is just localized in either of the two wells, right? Because that's lower energy than the top. But because this well is so shallow, if you include the quantum fluctuations of these two phonons, you just solve this by considering these 2 degrees of freedom as bosons. And the exercise is actually exactly solving a bosonic system inside a double well. Okay? If you do that, it turns out that the system still wants to be delocalized. So you look at the ground state wave function and you take the square, and it looks like this. So you see that the system is still living across the two wells. That's why this material is called quantum paraelectric, because it's due to the quantum fluctuations that you do not see any ferroelectricity for the unperturbed, unstrained system. So then the idea is that you take this mode and you couple it to a photon. Again, we do a single mode approximation, effective approximation. And now the coupling goes again as a P dot A, and it's scaled by the oscillator strength of this ferroelectric soft mode, essentially. And you can actually do this for a simplified model in the exercise. You don't have to do it now unless you don't want to have lunch, which I don't think is the case. And then this is just the starting point of the notebook. You have a double well, and you can look at the excited states, and you can see that this one is delocalized. The first excited state has a node, so on and so forth. Now, if you couple this into a cavity, and you do it for the low energy Hamiltonian that I showed you before, you get some funny behavior. In fact, you go from the case where the system is uncoupled, where you have this delocalized wave function. So you have a probability to find the particle across the double well. But at the moment that you increase this coupling strength, this probability in the center becomes less and less, to the point that you get actually a node. Okay? And actually what happens at this point is that the ground state of this Polaritonic system and the excited state become degenerate. So if you have two degenerate states, one in one well and the other one in the other well, or a linear combination of those, you can always diagonalize the problem and find a solution which is localizing only in one of the wells. And this is equivalent of saying that you can have a spontaneous symmetry breaking. So that means that the system gets localized by the cavity, and it will choose to be only in one of the two wells spontaneously. So any small perturbation will tilt it in one of the two wells. So, and that's the idea behind this ferroelectric phase transition aided by the cavity. And then, of course, this can be, so this is how the ground state and first excited state look like outside the cavity. So you have that they're definitely different. Okay, so this has no node, this has a node. But inside the cavity, these two become the same. Okay, and actually this works for a broad range of cavities. It doesn't need to have a resonant frequency to couple in to see this effect. You can see it also off resonant.
Just to be clear, the potential itself is unchanged.
The potential is unchanged in this picture. In principle, with temperature and the cavity couplings, which are very strong, one should also include the effects on the other phonons, which would change also the two phonon potential. But that becomes cumbersome. And at that point, we didn't have QED-EFT, but now we have, so that we can look at. But we haven't done it yet. But it would be interesting because there are more phonons involved in the transitions as well.
So can this be understood as a cavity modified ground state?
Exactly.
Landscape?
So you can understand this really as a modification of the ground state of the material because of the interaction of the fluctuations of the phonons with the fluctuations of the photons. And then this is just to motivate what you will see tomorrow. You can take this further, and then you could in principle include temperature. And the whole idea of cavity material engineering is really the possibility of engineering the material into different phases. So usually you have a phase diagram that has for sure on one axis temperature, maybe the other axis pressure, doping, whatever. But now you can have H0 as another axis, which is the light metal coupling strength. And then you could, by scanning through H0, access different phases of the material. So you could go from the quantum paraelectric to the ferroelectric or to the standard paraelectric and so on and so forth. And this kind of transition can also be affected by the temperature. If you're interested, you can take a look at this paper here. Or you do the notebook because there is also a part with the temperature dependence in the notebook. Okay, so that was supposed to be optional anyways, but you're very welcome to take a look at that because it's an access point to understand the paper and some of the things you'll do tomorrow. And then I think now you're free to go for lunch. And thanks for listening.